This is a first video discussing problems involving tests of the mean. So let's get right to it. Okay, so we're going to look at first of all, a test of the mean, but let's talk a moment first about going through these tests. The test of the mean involves, obviously, all 5 steps. It's a complete test. These are complete tests of the mean. And we have gone through what the structure of the hypothesis test is. So we've discussed these tests at length, with the exception of in step 3, how do we go about finding p-values or critical values? Okay, we'll emphasize that in all these problems. Because it's going to be done differently than what we talked about in test of proportion. So we're going to go through the other steps fairly quickly. So let's just proceed here. Let's read the problem here. A company provides tanks of liquid nitrogen to research companies. They want to test that the mean volume of the tanks is 50 liters. A random sample of 36 tanks of liquid nitrogen yields a mean volume of 48.5 liters and a standard deviation of 6.2 liters. Assume that the volume of liquid nitrogen is normally distributed. We'll kind of ignore that statement because we'll make the assumption that that is going to be true in all of the problems that we work. Test at the alpha equals 0.05 significance level. So I've highlighted in yellow the information we need for step 1, basically, for the claim and the significance level alpha. And the claim is that the mean is 50, which means that the mean is equal to 50. And then from that, we can build our null and alternate hypothesis. And we see that the alternate is not equal, since the claim included equality. This makes it a two-tailed test, which is important when we get down to step 3. The information from the problem that the mean was 48.5 and the standard deviation was 6.2 and the sample size was 36 comes into play in the test statistic. We substitute those in along with the assumed value of the mean from H0, the 50, and we get a test statistic of negative 1.452. And what we're interested in now is in step 3 and determining if this number right here is an unlikely number. So let's go down to step 3. When we deal with critical values here, remember that if the test statistic, if H0 tells us it's a one-tailed test, a left-tailed test, we're going to have one critical value on the left. If it's a right-tailed test, one critical value on the right. If it's a two-tailed test, one on each side of the mean. And this is a two-tailed test, so we're going to have one critical value on each side of the mean. And table A3 gives us critical values for T. 2 things that we need going to the table is we need to know what alpha is. Well, actually 3 things. We need to know that it is 2 tails, and we need to know what alpha is, and we need to know what the degrees of freedom is, because test statistic is identified by its degrees of freedom, which is a sample size minus 1, which is 35 in this particular case. So let's go to the table, which I have put down here. Just kind of attached it to this document so I didn't have to flip back and forth, although I'm still flipping back and forth. We see in this table A3, we see across the top two rows. One says area and 1 tail and some numbers. The other says area and 2 tails and some numbers. The numbers that we're looking at are are significance levels. These are values of alpha. We're not looking for an area in one tail because we're looking at a two-tailed test. So we're looking in area in two tails. And then what we're going to look for is alpha. Well, alpha was 0.05. So here's alpha, and that is at the head of a column of critical values, and that's where our critical values are going to be found. Our critical value is going to be found in this column. Now we need to know the row. Well, the rows are on the left here, and they are basically the degrees of freedom. Remember, ours is 35. So we're going to look in the 0.05 column for area and two tails, and we're going to look in the 35 row. And 35 row is right here, and we see that 2.030 is the critical value. One thing about this table is all these critical values that we have here are all positive. They are all on the right side. So we need to have one on the right side and one on the left. Well, this gives us the one on the right. 2.030 is a critical value on the right. The left tail is going to be the opposite of this. Anytime we need a left tail, we find the one on the right and change the sign. So the one on the right is the right tail, critical value on the right, in the right tail, and negative 2.030 is the critical value on the left side. So we've got our critical values, negative 2.030 on the left and positive 2.030 on the right. So let's go back up to our problem. And let's look at the picture here. What we do when we're dealing with critical values is we plot the critical values on a horizontal axis, and it's always a good idea to draw the picture and plot the critical values, negative 2.030 on the left, negative 2.030 on the 030 on the right. And usually we would have the mean in here. The mean is 0. It gives us the ultimate point of reference here. And then we are going to find the area underneath the curve to the right of the positive 2.030 and the area underneath the curve to the left of the negative 2.030. Okay, so I'm sorry, we know that the areas underneath those two curves, the two areas underneath the curve make up alpha. So the area to the left of negative 2.030 is half of alpha, 0.025 here. And the area to the right of positive 2.030 is half of alpha. And what we do then, having identified where the critical values are, we plot the test statistic to see if it is in a region that causes us to fail to reject, which is between the critical values. It's basically a likely value or farther away from the mean than one of the critical values. And in this case, it is not. So the critical regions are out in the tails. This is not out in the tail, therefore we would fail to reject in step 4. Okay, so that's how we're going to use critical values for this problem. And we see that our test statistic is not unlikely. P-values, okay, we're going to be using a function on the calculator to find p-values. And a p-value, remember, is the area underneath the, I'm sorry, it's a probability of observing a test statistic more extreme, which means farther from the mean than the test statistic. We need to know, first of all, is it a one-tailed test, left or right? Or is it a two-tailed test, which ours is? So once we've done that, we are going to go find the tcdf function. And the tcdf function, just like the normal CDF did, requires two numbers, Actually, it requires 3, but the first 2 numbers it requires are a lower bound for the probability, this p-value, and an upper bound. And this little blurb down here, and it's in each problem that we're going to look at, identifies what numbers we're going to use for our for finding the p-value. If it's a left, I'm sorry, a left-tailed test or a right-tailed test or a two-tailed test. So let's look at, and you can look at this at your leisure. You can freeze the video and spend some time with that. But we're just going to look at the two-tailed test situation here. Now the test statistic is going to fall on one side of the or the other of the mean, 0. If it's negative, it's on the left. If it's positive, it's on the right. What we're going to find is the area underneath the curve farther from the test statistic, or farther from the mean than the test statistic. So what we're going to do then is, since it's on the left, our lower bound is all the way to negative infinity, but we'll just use a large negative number. And the right upper bound is going to be the test statistic itself. Okay, so we're going to find that area, and then we're going to multiply that by 2. If that test statistic were on the right, we would find the area underneath the curve farther to the right of the test statistic. And the lower bound would be the test statistic, and the upper bound would be positive infinity, or a large positive number. So we're going to have negative infinity for our lower bound, and the test statistic negative 1.452 for our upper bound. And then once we find that area, since this is a two-tailed test, we have to multiply that area by 2 to get the p-value. So let's go look at the calculator here. And do that. All right, so the tcdf is found under second vars. So we'll do second vars. Oops. Second vars. Oh, it's still not doing it here. Let me go back and I'll just do it this way. Second vars, and then we want number 3. I'm sorry, number 6. Second vars, number 6, because we want tcdf. Since this is a test of the mean, it's all about t. And now we need a lower bound. First number that goes in there is the lower bound. And since this is on the left, we're going to start with negative, large negative number, comma, and the test statistic, which was negative 1.452, comma, and the degrees of freedom, which was 35 in this case. Close the parenthesis. Oops, I left a parenthesis out. Comma, 452. Oh, I've got it. Never mind, it's there. And then enter. And there is the area underneath the curve farther from the mean than the test statistic on the left. But remember, this is two-tailed, so we have to multiply this times 2. And that is our p-value. This is not the p-value because it's a two-tailed test. We only found the area on to the left. We have to multiply it by 2 to get the p-value. And that's how we're going to find the p-value on the calculator using a tcdf. Let's go back and look at our document. And then once we've got our critical value, we found that the test statistic was not in a critical region. And we found that the p-value is 0.1554. Now we go to step 4, and we compare the p-value to alpha. If it is less than or equal to, we'll reject, but it is not, so it's greater than, so we'll fail to reject. And the test statistic was not farther from the mean than the left critical value. Therefore, we're going to fail to reject it. It's not in the critical region. And then we go to our flowchart in our tables and formulas handout, and we state our conclusion. In this case, because the claim included equality, that means it's not about supporting or not supporting, it is about warranting rejection or not warranting rejection of the claim. And so it wasn't rejected. There is not sufficient sample evidence to warrant rejection of the claim that the mean is equal to 50. Now, we have a test on the calculator, and what the test on the calculator does is it basically gives us the answers to steps 2 and 3, but it only covers p-value. It does not have anything to do with critical value. So if we run the test on the calculator for a test of the mean, it's going to be the t-test, which is number 2 in our list, and we'll go to it in just a second here. And it will give us the test statistic value. And in output, it'll give us the test statistic value, and it will give us the p-value. We just have to make sure we get the inputs to this thing correct, and it requires the assumed value from H0, which is 50. It requires the mean, standard deviation, and sample size from the sample information, and it requires the identification of the relationship in H1. And then once we have that, we get our results. Again, those two, the test statistic and the p-value, are the two that are important that come out of this. And let's go ahead and look at this then. Let's just come back to our calculator. Let me clear this out. And remember where our test is. The test is under stat, right arrow to tests, and a number 2. If you recall, in a previous video, the test on the calculator for proportion is the 1-prop-z test, number 5, and I told you should probably just memorize that. Test of the mean is a t-test, it's number 2, you should probably just memorize that. So I'm going to hit number 2. Stats is highlighted. This basically says that the sample gives us things like the mean and standard deviation of sample size. If all we had was the actual data and no statistics calculated for us, we would use data and tell it what list we had put the data in, and it would calculate those separately. We still need the null hypothesis value, which in this case is 50. We still need, whether we're data or stats, we still need the relationship in the alternate hypothesis, which is not equal to. And you'll see that I've already put the data in for all this. And then I come down here, and if I hit calculate, I will get the test statistic and the p-value along with some other stuff, but those are the two important things. But if I hit draw, if I go over to draw and do that and hit enter, I get the p-value sketch as well as the test statistic value and the p-value. And it has gone through and it has found the area underneath the curve farther away, and on this case, the left, farther away from the mean than the test statistic, which was negative 1.452, and it doubled it to get 0.1555, okay? All right, I think that concludes then our step I'm sorry, our first problem. And let me stop recording here for a second. And we'll continue on with the next problem in the next video.